Hi, in this tutorial we are going to solve a question related to reactions of alkenes. We have 5 sets of reactions, and in each reaction we have an alkene and another reactant. And in the question we have to provide the structure of products. Let's look at the first reaction. In the first reaction we have an alkene and HCl, a halo acid, and the product is going to be an addition product, and it will follow Markovnikov rule. What is Markovnikov rule? When we add HCl or HBr to an alkene, hydrogen will be added to the side of alkene where we have more hydrogen or fewer substituent, and the chlorine will be added to carbon where there are less hydrogens or more substituent. Let's write the product for the first reaction. And here we have a cycloalkene. It's a cyclohexene, 1-methyl cyclohexene. After the reaction, let's write the cyclohexene here, CH3, and hydrogen will be added to this part, and chlorine will be added to this part of double bond according to Markovnikov rule. So this is going to be Cl. So this is the major product. The minor product will be the anti-Markovnikov product. Okay, let's move to second question, or second part of the question. We are adding halogen, a halogen molecule to an alkene, and we are going to produce a 1,2 dihalide. So basically, as similar to the first reaction, we will add Br and Br here on the two sides of double bonds. But when we are adding bromine or chlorine molecules, the addition is stereoselective. Trans addition has to takes place. So let's draw cyclohexane, and let's draw methyl. But before drawing methyl, let's see, since we are going to add Br and Br to each side of double bond, and Br, they have to be on the opposite faces. Let's say that this Br will be added on the out of paper plane, and the other bromine has to be added as dash or going inside the paper plane, and we have to add here methyl group. If Br is dash here, methyl group has to be drawn as wedge. So this is our major product. So we got 1,2 dihalide product. Let's move to the third question. In the third question, we have an alkene, and we are adding bromine in the presence of water molecule. So the difference between the previous option and this one, we are carrying out the reaction in the presence of water. So instead of synthesizing a dihalide, we are going to synthesize a halohydrin. And one part will be Br, one part will be OH, but let's decide which one will be OH and which side will be Br, because this is not a symmetric alkene. We have to write the major product, which is going to be the more stable product. Let's write here alkene. First, I want to write the intermediate. The intermediate will be bromonium cation, a cyclic bromonium cation, and then we will have Br minus plus we will have still water. Okay, the product. So the product will be based on which carbon we are going to add water molecule, or at the end it will be OH, but let's say most of the time the attack of water as a nucleophile will occur to more substituted carbon. The reason, during the transition state, there is going to be partial charge development here, and this carbocation will be like a tertiary carbocation. It will be more stable. So that's the reason why we need to add OH here and Br here. So let's draw the final product. And the addition has to be a trans addition, because Br and OH has to be on the different face of the ring, because we are forming here a cyclic bromonium ion. So let's say Br is going to be wedge, and OH has to be dash because it has to be trans, and OH, and here we had a methyl, and this group has to be wedge because we chose OH to be dash. Okay, so this is going to be our major product. So let's again look at what did we get. We get a halohydrine. One part of the double bond will be substituted with bromine, and the other will be OH. And OH and bromine has to be like radius selective. OH has to be added to the more substitute carbon. Okay, let's move to the next question. In the next question, we have an alkene. Here we have mercury acetate, water, and sodium borohydrate. This is oxymercuration-demercuration reaction. What is oxymercuration-demercuration reaction? Basically, we are going to add water to double bond according to Markovnikov rule. So let's write the product without going through the details of reaction mechanism. We have here cyclohexane. This will be methyl, and hydrogen will be added here, and OH will be added to this carbon according to Markovnikov rule. Okay, let's look at the last option. In the last option, we have an alkene, and we have here borane, BH3, peroxide, and hydroxide ion, and definitely this is a hydroboration reaction, hydroboration oxidation reaction. This is going to produce an alcohol from alkene, and the addition has to follow non-Markovnikov rule. So basically the opposite product if we compare the previous option. So hydrogen will be added to carbon with less hydrogen, and OH has to be added here. So let's write here CH3, and this is OH. So up to now, what we have done, we have done 5 different reactions. In the first, we added a halo acid. It follows Markovnikov rule. Second, addition of bromine to an alkene. It follows trans stereochemistry. The added BRs has to be trans with respect to each other. The next reaction was addition of Br in the presence of water. This will generate a halohydrine product. One part of the double bond will be substituted by OH, the other one will be bromine, and the addition has to be trans because the intermediate is a cyclic bromonium ion, and hydroxide or OH group has to be added to carbon on the double bond with more substituent. Then we did an exercise with oxymercuration-demercuration reaction. It is Markovnikov product, and the last question was related to hydroboration oxidation reaction. Hydroboration oxidation reactions yield a non-Markovnikov product. Basically, hydrogen will be added to carbon with fewer substituent. Sorry, the opposite. Hydrogen will be added to carbon with more substituent, and OH will be added to carbon with fewer substituent. Thank you so much for watching.